All right, and we are live. Welcome to the Cool Data Project Show, where I interview practitioners in ML, DL, and AI about interesting projects that they're working on. Today, we have my friend Harpreet Sahota, who is going to introduce himself. He has a full presentation. We previously had audio issues, so we're hoping that today goes great, and I am just going to let him take it away.
Awesome, Kristen. Thank you for having me. And fingers crossed. I pray to the presentation gods that everything goes as planned and that we don't have any issues. I'm gonna go ahead and share my screen here. Hopefully, you guys will be able to see it, and we'll share the entire screen here. You should be able to see a desktop, and now
Yep.
on this desktop, you will see a presentation. All right, what is up, everybody? My name is Harpreet Sahota. I am the Deep Learning Developer Relations Manager at Deci. Actually, I'm the entire Developer Relations Department at Deci. But I'm here to talk to you about lessons learned from building YOLO-NAS, which is a foundation model for object detection. So let me just tell you a little bit about myself before we jump into this. My background is pretty quantitative in nature. I studied math and statistics in grad school, undergrad, worked as an actuary, as a biostatistician, as a lead data scientist before moving over to DevRel. Worked at a number of companies in DevRel, Comet, Pachyderm, now at Deci, as well as various contract engagements. Born and raised in Sacramento, California, and I'm not a cringy LinkedIn influencer. So today's focus, though, is going to be on sharing the story of YOLO-NAS from an outsider's perspective. So when I say outsider's perspective, that means, I wasn't involved in the research or the engineering aspect of YOLO-NAS. I was more involved in the developer relations and developer experience aspect of it. So kind of making the model as easy to use and user-friendly as possible by providing feedback to the team. But I just want to be able to connect kind of the technical aspects of YOLO-NAS with kind of the technology that helped bring it forward and the lessons that we learned while developing YOLO-NAS. So that's what we're going to talk about today. We'll do an introduction to NAS. We'll talk about the path we took to building YOLO-NAS, talk about YOLO-NAS as a foundation model, and some key challenges and lessons learned in building YOLO-NAS. So let's go ahead and jump into the journey of building YOLO-NAS. So NAS, N-A-S, that stands for Neural Architecture Search. And so applying neural architecture search to find a new state-of-the-art model for detection is something that the research team at Deci has been wanting to do for a long time. But it turns out that this is a challenging task. And you'll see why it's a challenging task after I briefly explain what neural architecture search is. So first, let's talk about the few different generations of neural architecture search. The first generation is this kind of random evolutionary search type of methodology. This was kicked off in 2017 with NASNet, which achieved state-of-the-art results on ImageNet. And these techniques, this first generation, the techniques here were really all about exploring a vast search space of architectures. These methodologies were pretty straightforward, and they relied on random sampling or kind of evolutionary algorithm type of principles. The second generation of NAS is where we started to move more towards performance and platform awareness. So, as time went on, as deep learning became more advanced and kind of more integrated with our everyday technology, there was an increasing need to deploy models on devices with limited computational resources. And these are devices like mobile phones, IoT devices, or edge servers. And so there came a need now for neural architecture search methods to optimize for accuracy while considering platform specific constraints. And what do I mean when I say platform specific constraints? Some examples of that include flops, floating point operations per second, and this is just the measure of computational cost of a model. So reducing flops is going to speed up model inference, but you might do this at the expense of accuracy. Then there's model size, right? So the memory footprint of a model is crucial for devices with limited storage. Then there's the issue of latency. So latency is the time it takes for a model to produce an output, and this is really important for real-time applications. And then finally, energy consumption. Most edge devices like a phone are battery powered, so you don't want a model to be performing inference and then just drain the entire battery of your device there. And so that's what the second generation of NAS was focused on, trying to find architectures that strike a balance between good accuracy and meeting the platform constraints. And so this trend kind of continued to grow with the third generation of NAS. And third generation is more about faster and more robust methodologies. So this came through by methods like weight sharing and zero-shot NAS. So weight sharing is, instead of training every architecture from scratch, weight sharing allows you to explore different architectures that share weights in the search process. So it's going to reduce the computational overhead of evaluating a number of different candidate architectures. Zero-shot NAS meaning will predict the performance of some architecture without even training the model. And so this is usually achieved by training a performance predictor on a subset of the architectures, and then using this predictor to estimate the performance of the new architectures. And so at Deci, there's something that we have, our proprietary technology. It's called the AutoKnack Engine. And this is kind of like a new era of neural architecture search because it's hardware aware and data aware. So the AutoKnack Engine has algorithms for predicting neural network model accuracy without training the model, and it makes it possible, to do really fast and powerful search strategies over your design space. And so now that we kind of motivated what neural architecture search is, let's talk about how it is kind of actually done. So neural architecture search involves a few fundamental components. One is the search space, next is a search strategy, and then a performance estimation strategy. So the search space is just the set of all possible architectures that your algorithm can explore. And this could be as simple as the number of layers in a network, or as complex as the types of layers, the connectivity and connection between layers, and various other hyperparameters. In the case of YOLO-NAS, which is hardware aware and data aware, we considered a number of different components in the inference stack. This is like, the intended hardware, T4 for YOLO-NAS, the different compilers and quantization techniques. So how you design a search space is really going to influence the effectiveness of the NAS process, because eventually you have to traverse the search space. And so you traverse the search space using a search strategy. And so you can use various methods here. It could be like a random search, Bayesian optimization, reinforcement learning, evolutionary algorithms, gradient-based methods. There's a number of methods out there. And of course, the methodology you choose is going to affect the quality of the solutions and how long it takes to traverse that search space. Then there's a performance estimation strategy. Right. So after we get a architecture generated, the neural architecture search mechanism needs a way to estimate this model's performance. And so this could be as simple as training each architecture on the data set and measuring its performance, or it could involve more complex and computationally efficient strategies, something like, learning curve exploration, one-shot NAS, weight sharing that we've talked about previously. And so the output of this neural architecture search algorithm is typically going to be an optimal or near optimal neural network architecture, and optimal in the sense of, whatever defined performance metrics that you set in place. Once you've got that, the architecture is going to be ready to be trained on a full data set for that task. And, the task could be anything from object detection, image classification, language models, code generation, what have you. But the goal is to ultimately discover a network that performs better than a human designed architecture, or at least improves upon them by kind of optimizing for various trade-offs. So kind of a high-level overview of how AutoKnack works. So we have a search space that is going to be defined by a list of features, and then for each feature, some list of values. And feature here is going to be like a part of the model architecture. So if you have a model that you're building, and this model is maybe like, some type of encoder decoder architecture, and you have like, a backbone for that type of architecture, and you can specify like, for stage 4, I want to have some number of channels, 16, 32, 64, what have you. That would be the feature. Stage 4, number of channels with the different values. And so the combination of all these features is going to form your search space. Typically, you'd start off with 20 to 40 features that you define, but then you end up taking like a Cartesian product of all those features, and then you end up with like an astronomical number of combinations, anywhere from 10 to the 10 to 10 to the 30th. And then from there, you take a subsample, typically between 10 to the 6th or 10 to the 8th possible combinations. And this is going to be your new architecture search space. Once you have this new architecture search space, you then need to benchmark the model performance in terms of accuracy, latency, or whatever metric that you choose. So, for example, if you have like a search space of 10 to the 7th models, and then it takes you 2 minutes to benchmark a single model, that would take something like 40 years for you to benchmark models. So instead, what we do is we benchmark some of the models, and then from there, we're able to predict the potential for all the models. And so that brings us to this like accuracy potential prediction step. So basically, given an AI model, we predict 2 estimators for the model, one for the accuracy and one for the runtime performance. And then you get like the one with the best predicted performance, and you train that one, and you're done. And so this is kind of the process that we use to discover the YOLO-NAS architecture. So let's talk about the YOLO-NAS architecture. So this is actually the search space that we had, right? The features that we fed into our AutoKnack engine were really heavily inspired by YOLO v6 and YOLO v8. We also use some new quantization techniques. So we suggested that we should try to use some quantization-friendly basic blocks that would then generalize. We had a search space of 10 to the 14th. This is the size of our search space. And from this search space, we were able to identify 3 networks, small, medium, and large version of YOLO-NAS. And the time it took to this entire AutoKnack process that we took was the equivalent GPU time of training, fully training 5 networks. So we were able to efficiently traverse that space. Then we trained the model with supergradients, which is our open source library. Then we provided a new and advanced training regime. So we pre-trained on Object 365, as well as Cocoa. We used some pseudo-labeled data. We applied knowledge distillation from a pre-trained teacher model. And then we, implemented quantization for blocks. So then after the training, we applied post-training quantization and converted the network into int8 precision with a minimal loss of accuracy. And so this is kind of the essentially the kind of an illustration of the Nash process. So on the graph here, you see a plot on the top here, accuracy versus latency for all the models. And what we do is we choose the models that are on the frontier, meaning up and to the left. And those were like the best models. So to kind of define some of the terms that you see here, I'll quickly go through a few of them. Cross-stage connections. So when you're designing a deep neural network, it's structured in a layered model, a layered manner. So sometimes these layers are grouped into stages that are based on their functionality. So for cross-stage connections, if you want to imagine like a factory assembly line where different sections or stages of the line are responsible for different parts of assembling a product, instead of passing the product from one section to another, sometimes you want to directly connect an earlier section to a later one, and you want to bypass some middle sections for whatever reason. This is going to help combine the different product features or aspects more effectively. So in neural networks, these direct connections between the different stages are going to help the network learn and combine features more efficiently. Quantization aware rep VGG blocks. So rep VGG is just a neural network architecture, and so quantization is a technique that simplifies the values inside of a network, like the weights, to smaller precision values, and it ends up making the model faster at inference. So you can think of quantization as rounding off numbers to make calculations simpler and faster. So putting all this together, quantization aware rep VG blocks they're kind of special units of a factory assembly line, these rep VGG blocks, and they're designed knowing that the final product is going to be simplified through quantization. SPP, that's spatial pyramid pooling. So this is a technique using neural networks to process input data at different sizes so that you can capture information at different scales. And I can continue going on here. So real quickly, and if anyone's got questions later, just let me know. But the neck, so in the structure of deep learning models, especially those that are defined for visual tasks, the neck is the portion of the network that sits between the main feature extraction component, which is the backbone, and then the final prediction layers, which is the head. So the neck is, responsible responsible for typically refining and processing the features before making predictions. So inside the net, we have a path aggregation network, and this is just improving the flow of information within the network. So it's enhancing the way the different layers or stages of the network are communicating with each other. This bidirectional top-down, bottom-up information flow kind of says what it means there. So information is going to be processed in two directions, from the lower layers to the upper layers, meaning bottom up, then from the upper layers back to the lower layers, top down. So this bidirectional flow is going to ensure that all parts of the network can share and benefit from the information that was processed at different levels. So kind of moving on, why create another another YOLO model? Well, Deci's got a strong research background and a strong research culture. I think something like 30 to 40% of the company has some sort of advanced degree, and a large percentage of PhDs. So there's those obvious research-driven reasons, right? We want to push the frontier of accurate and fast detection models. We wanted to build a model that was suitable for fine-tuning on any data set, and we wanted to educate people on the power of neural architecture search and the importance of having hardware-aware model architectures, and build a object detection model that was quantization friendly. So real quick, let's talk about evolution of YOLO. So prior to YOLO-NAS, the current state-of-the-art models from the YOLO family were YOLO v6, YOLO v7, YOLO v8, right? So our goal was to create a new quantization-friendly architecture that was inspired by the success of these modern YOLO architectures. So the initial step in neural architecture search was to define the search space, right? And then for YOLO-NAS, we incorporated the basic blocks into the search space, incorporated the basic blocks from YOLO v6 and YOLO v8 because they generalized well. Then we applied our AutoKnack Engine, and this allowed kind of for the intelligent exploration of the search space that's 10 to the 14 possible architectures. So definitely influenced by the previous work that came before us. But also the fact that object detection is extremely competitive, right? So is highly competitive subfield of computer vision, right? There's teams around the world working on object detection, benchmarking on COCO, use T4 hardware, and they're all striving to make state-of-the-art detection model. Like it's not like a dead area of research. Shout out to RoboFlow and Peter Scholarship on this graphic. I absolutely love it. But yeah, we wanted to compete, right? So that's we wanted to put our foot in the ring, and we wanted to show that we could bring a state-of-the-art results and we could win in this competitive task. And I think the results show that we kind of got there, right? We're being state of the art, but we're not by like a huge version. We didn't exceed the state of the art by 2x or 10 MAP, but it's an incremental improvement. But incremental improvements, they're groundbreaking, right? This is like sprinters that were working to shave milliseconds off their times. The point was not to show that we can dominate specific task or data set, but to show that we have the solid technology team and know how to dominate on any task, any hardware and data set. So there's that competitive element which I absolutely love. We're out here trying to do this, make it happen. And the end result, like I mentioned, was 3 final architectures: small, medium, large versions of YOLO-NAS, and these are performing pretty well. We've got some outstanding results with these new quantization friendly blocks. So when we talk about YOLO-NAS as a foundation model, like what does that mean? So, it had a multi-phase training process, and it included pre-training on Object 65 and pseudo-labeled data. And then on top of that, we used knowledge distillation and distribution for loss. Object 365 is a very comprehensive data set, 2 million images, 365 categories, and we trained for about 25 to 40 epochs on Object 365. Then using the COCO data set, there's also some unlabeled images, for the COCO data set, 123K of those. We generated pseudo labels for those using a pretty accurate model, and that accurate model in our case was YOLO-X. So we used YOLO-X to create labels for COCO data test set, and then furthering on that. Then we have acknowledge distillation, right? So we acknowledge distillation term to the loss function, which then the student network able to kind of mimic the teacher network's logits, and then we use distillation focal loss. So we learned box regressions as a classification task, and then we discretized box predictions into finite values, and then predicted distributions over those values. And so right there's a QR code. I think this will take you to our technical blog that I wrote a while ago. So if you'd like to scan that and read more, go for it. So that's how YOLO-NAS, and there's some obvious challenges that I want to talk about that we faced, that we learned a lot as a company when building YOLO-NAS. So one is performance benchmarks, right? Existing YOLO models are very, very performant, highly performant. So it's a challenging task to kind of surpass those models, especially on the T4 hardware. Being hardware aware is also a challenge as well, because we're applying end-to-end hardware NAS on detection. It's rare and has its unique set of challenges. Building a model architecture that was quantization aware while maintaining high accuracy was also quite challenging as well. And then fine-tuning, right? We would need to develop a strategy that would be suitable for fine-tuning across various detection tasks. And so, one of the biggest challenges was working with the RoboFlow 100 dataset and benchmarking on that. So RoboFlow 100 is 100 separate datasets. And so there's a lot of uncertainty that we're facing on the model's performance on downstream tasks. We didn't know how long it would take to train or evaluate on all 100 datasets. And then on top of that, they had this rule on RoboFlow 100 that you couldn't tune hyperparameters for individually for a specific data set. So you kind of had to use global hyperparameters across all 100 data sets. So obviously, you can imagine that that's quite challenging to do as well. But, we figured if we can make it on RoboFlow 100, we can make it anywhere. Because, successful performance on this, makes a strong case for the ability of YOLO-NAS to adapt to these different downstream tasks. And if you look at the RoboFlow 100, like there's 100 different data sets, and they're all varying from, you have microscopic data sets, like, detecting microscopic images, detecting microscopic objects in images, as well as detecting video games, things like that. And so we did pretty well. Like we didn't like 2x or 3x the state of the art. But we made an incremental improvement with our small and medium models over the current state of the art. And so just a little bit of technical detail. Here's another link to, actually this might be the technical blog. I think the first link might have been just to the announcement blog, but this should be to the technical blog. So we trained YOLO-NAS using a learning rate of 5e to the 4 for the small version, and then 4e to the 4 for the medium version of the model. We used weight decay, 1e to the 4. We excluded weight decay on the bias and Bashnell layers. We used exponential moving average with a decay factor of 0.99, batch size of 16, and image resolution of 640 by 640. And so some other challenges we faced was model delivery, ablation studies and results expectations. So for model delivery, managing issues encountered during the model discovery process was something that we learned, right? So we need to find some way to adapt from the state dict from the checkpoint and ensure that the network will compute the same when it's in its PyTorch or OnX versions. Ablation studies as well. We're deciding what to share publicly from ablation studies and experiment logs, and considering the potential impact on how the community would perceive the product was also challenging. Results expectation, managing expectations for results in the face of known issues like image size constraints, impacting performance. But through these challenges, we learned a lot of good lessons. So code migration being one. So the research might begin using any code base, but as the project kind of progresses, this work should migrate to a standard code base. In our case, that would be super gradients code. So that streamlines development and maintenance as project matures. Benchmarking evaluation, right? So follow the handoff between teams. We need to conduct a comprehensive benchmark and evaluation to ensure that the performance is meeting our expectations. Also, protocols for collaboration, right? There we learned that we needed some very clear protocols that defines, rules for who's passing the code, how code is being passed, how written material regarding the model is going to be generated and passed between teams. Documentation. So, each document that's associated with the project should have like a clear purpose, clearly state the authors, the schedule for delivery, and outline the process for creating that document. And this, I think, will help us ensure that all necessary information is captured and understood by the team members. Also, just the cross time zone collaboration, right? We're working across time zones. Like I'm based here in Central Time Zone. Deci's in Tel Aviv. That's like an 8-hour time difference, right? So it's important to really sync work hours between reasonable limits, right? So we're trying to create a window of overlap that's at least 4 hours, and shift tasks that require other teams' attention into that window. It's a lesson that we're still learning, but it's challenging to do. We also have some great triumphs after releasing the model. So we set out to achieve a new state of the art, and we got there. We're able to increase visibility of our training library super gradients. We 10x the pip installs, 4x the GitHub stars. The community seems to really embrace YOLO-NAS. We got a lot of good inbound leads from launching YOLO-NAS. Issues were being open on GitHub, which we had none of that before, and that gives an indication that people are not only using super gradients, but they care about the direction of super gradients, and they care about where it goes. And so this gives us better insight into what the community wants. We're getting contributors now from outside of Deci, and so it's been cool. Yeah, it's been great. Like the reception from the community, and you can expect more open source from us coming in the near future. So just real quick, if you're interested in a quick start in super gradients YOLO-NAS, if you scan this should take you directly to a notebook that I authored, which will give you it'll give you like a breakdown of how super gradients works through the lens of using YOLO-NAS. So definitely check that out. It'll be you'll see how to use a pre-trained YOLO-NAS for inference. You'll understand how recipes are used in YOLO-NAS. You see the end-to-end deep learning training framework and how we use advanced techniques like automatic precision, exponential moving average, quantization, knowledge distillation, all that stuff. We've got that going on in super gradients. And it's a quick start, real quick, just like a few lines of code and you're good to go. And we offer a lot of flexibility. So it's super gradients is a PyTorch-based training library. So it's sits right on top of PyTorch, abstracts away a lot of boilerplate code. That means it also gives you the flexibility of writing native PyTorch. You can use data loaders how you see fit. You can define your own custom loss functions, your own custom metrics, and all that stuff. And so this model.predict is it's a feature that I could say I push the team to create. If we don't have an easy way to do prediction, nobody's going to use the library. And really glad the team took my feedback and made it happen. Yep. So top takeaways from YOLO-NAS. So in the NAS process, having hardware awareness when designing your models is crucial. We did some interesting stuff with head replacement for fine tuning. If anybody has questions, we could chat a little bit about that. Use quantization where blocks to prevent accuracy drop when we quantize the end date. And then you use a lot of advanced training features from super gradients to get to that state of the art performance. And again, here's a QR code that will link you to the quick start. And feel free to connect with me on Twitter as well. And that's it. That's it about YOLO-NAS. Alrighty.
Awesome. Perfect. Thank you so much. I really enjoyed watching that. Have you done something cool with it yourself?
Well, I've done a number of like Kaggle notebooks. So I'll publish that out there. But I've just really been impressed by what like people in the community have done with YOLO-NAS in such a short time that it's been out there. I interviewed actually somebody from the community last week who uh, used YOLO-NAS. So what he did was his name is Mohammed Moeen, and he's got a YouTube channel. I'll link to it in a second here. But he hooked up YOLO-NAS to ChatGPT with a Streamlit interface. So you drop in a picture of some food, and it's going to identify what's in there, the different vegetables and stuff that are in there. And then it'll pass those detections to ChatGPT, and it prompts ChatGPT to create a dish and present the recipe for that dish, and you get it right there on your
And the
Streamlit app.
recipe. Do the
Yeah,
recipes
yeah,
like look like I don't want to say look good because I mean I'm not talking about like from a food perspective. I'm talking about do they come out looking like something
yeah.
you could actually cook?
Oh yeah, yeah. They looked legit. They looked absolutely legit. So that was a cool project I saw somebody make. Where I've seen somebody apply. I think his name was Nate Haddad. Nate Haddad put YOLO-NAS into his tracking library. That was really really cool to see as well. We're working on getting YOLO-NAS to perform as well as it performs on T4 on the Jetson, which
Mm.
is challenging tasks. But we're getting there, and as soon as that's done, I'm looking forward to getting that spun up on my Jetson and playing around with that.
Nice. So you guys already have it running on a Jetson and you're just trying to optimize it.
We're trying to, uh, yeah, pretty much. We need to make tweaks to the architecture in order for it to be performant on Jetson.
Oh
But we're
yeah.
getting
No,
there.
I know all about the lag there. And
Yeah,
yeah.
yeah. And we're working on the segmentation and pose estimation
Mhm.
versions of YOLO-NAS as well, so they'll be coming out. But my projects were pretty simple and straightforward. Just doing some Kaggle notebooks and things like
Mhm.
that.
Well, if you need me to do backflips with pose estimation once that comes out, let me know. I got you.
Awesome. I will holler. Absolutely.
Awesome. And so, if somebody was looking to get into working with computer vision or maybe even just machine learning or ML ops, what advice would you give them?
Yeah, my advice is always like, you know, I've been a mentor for data science dream job for a very long time. And I
Are you
stopped
still
doing.
a mentor for data science dream job?
No, no longer. But I spent three,
That's
4 years, 4 years being a
going. Yeah.
mentor. And the biggest fallacy I think people have is like, oh, I need to like start from the bottom, and I need to know linear algebra and differential calculus and all this stuff before I even touch deep learning. And I don't think that's true. Like, I think you can have a top-down approach, right? I think just pick up, start with a notebook of YOLO-NAS. Start with a library like Super Gradients that abstracts away a lot of code, and just see the magic and get inspired, right? Like, I think when you're first starting out, that is crucial. Is if you start just by reading linear algebra books and differential calculus and all that stuff, like how long
Tired.
is it going to be until you build something with it? You're going to lose motivation. So I think as quickly as possible, just build something, get an application running, see the power, get inspired, and then go deeper if you need to. If you're like, oh, this is pretty cool, I want to learn more. How did this happen? Go deeper, and those materials are available for you. They're abundant. But yeah, I think people with that gatekeeping mentality need to just be quiet, man. Like just just don't
No, and I
discourage
get that.
people.
Yeah, I've probably forgotten more linear algebra than I remember. And, that has nothing to do nowadays with the programs the libraries are so high level that you're working with that you can go in and build something. And so maybe that's starting with a pre-trained model, but then you train on your custom data, and then maybe you're doing hyperparameter grid search, but there's like a layer of abstraction between that and the actual math that is involved. And so you can get pretty far. Not saying, I mean, I have a bachelor's in math and a master's in statistics. I love it so much. But the truth is, you can build things that have practical applications without necessarily needing to spend 4 years studying math before you hop into ML.
Absolutely, absolutely. And even when you do, like, say, oh, I want to get deeper into the math, then I wouldn't just pick up like a math textbook. I would pick up something like my favorite is like I love the manga series of like, there's a series of manga books that teach you how to do math and stuff like that. There's one for linear algebra, one for calculus, one for like statistics, and one for regression and things like this. Like, pick up one of those books and kind of get exposed to it gradually. But I think the name of the game is just get inspired and get interested, and that will propel your kind of path forward.
Now, are those books specifically teaching the math for ML or
Oh no, just general, just yeah, in
just
general, yeah,
general? Okay,
yeah,
just double
yeah,
checking. Double checking.
yeah, yeah.
Well, Harpreet, thank you so much for joining us today. I really appreciate, especially the perseverance coming back and doing this for the third time. But this, I heard you so well this time, and I really appreciated
Yeah.
the presentation.
Awesome. Thank you so much for having me. Appreciate it.
Yeah, awesome.
Cool.
Bye, everyone. Thank you for coming.
Cheers, everybody.